units, then automatically easily to get 40 to 50 marks, because that's not a joke. Because see and refer in the previous papers, a number of theorems, first 3 essays is given in the first 4 units, 6th, 7th unit is also there. Tomorrow we will discuss one more important theorems, Horn-Banach theorem and open mapping theorem, closed graph theorem. These 3 theorems we will discuss on tomorrow's class, and the last 2 classes on the next week, because completely we will discuss the operators through the Hilbert space and some other inequalities. What is the Hilbert space, and some other inequalities are also discussed. That is the Gram-Smith orthogonalization process, that theorem, and according to that theorem, we will discuss some other problems. Okay, and also at the same time, normally the same time Hilbert operators. We will discuss the Hilbert operators in the last 2 classes are there. Okay. Now there are 2 essays given from the operators. There are 2 essays given in the final examination and 2 short answers, because that is also projection theorem and some other Hilbert spaces, Hilbert basis theorem. Okay. Now these theorems are also referred in operator theory. That is the paper 11. Okay. When you must understood through the topology and functional analysis especially, then automatically easily to understand the operator theory paper when you choose the elective that paper. Okay. Now that is the paper 11. Okay. Now these sessions, because only already 4 classes are completed, remaining 4 classes very much more important session. Now, especially this class, fourth unit, this is also one of the important session, and remaining some other theorems are also discussed from 6th, 7th, 8th unit. That is one of the Horn-Banach theorem and its applications, and open mapping theorem and closed graph theorem. And according to those theorems are applicated, we will discuss some other applications depends upon the theorems. Okay. Students, listen carefully. Now, this is the above theorem of the proof is there. When you are given the normal linear spaces, suppose that the set capital S equal to set of x belongs to n, you are taking any one of the element or any one of the point x being any one of the normal linear space of the part, then their norm is unit. So that set is denoted by capital S. Then given the set of the norm element, when it is the unit, that given the set is compact, so automatically that is also a finite dimensional. First of all, you have to choose any one of the bounded closed set of normal linear space, that is capital A. Here A be any bounded closed subset of normal linear space. Now already we know that the above theorem, closed bounded sets are compact of a normal linear space, then it is finite dimensional. Here small r be any one of the element, or that element is denoted by radius. That there exists of the element is r is greater than 0, such that here r represents the radius, then their norm is less than or equal to r. Because here center now that then their norm is defined from the origin. Now here the distance of the norm is less than or equal to r. Here r be its radius. So radius, when the radius means it is radius, when you have to discuss, then automatically that is the closed ball is there. Closed ball means closed sphere. Okay. So here x be any one of the element given the closed bounded subset of capital N. So when it is conditional in the closed ball is referred capital B of. Now this is also defined from center it origin. Origin, we are taking the element is origin and the radius is small r. Now this norm condition refer the closed ball is capital B of 0. 0 means center at origin and the radius is small r. And given the origin, when the radius is we are taking, because that element then their norm is 1. So that closed ball is 0 and 1 is compact by hypothesis. Because then according to similarly it follows that when the radius of the value is taking at 1, so replacing in the same manner B of closed interval 0, r is compact, because open cover has a finite subcover is there. So this is closed bounded set. When it is compact, automatically it is a finite dimensional in the above theorem is there. See and refer the above theorem. A is closed subset of the compact set capital B of closed interval 0, R is compact. So the above statement is also given. So in sometimes this is also one of the statement. Closed bounded compact set B of 0 and R is finite dimensional through normal linear space. Sometimes that question is also given and also in the same manner that question is also repeated in this process. Okay, capital B of 0 and R, hence it is a compact. Consequently, every bounded closed subset of n is compact, then automatically n is finite dimensional. Okay, please stay on the line. Okay, students. Okay. Now, see the another one. Students, respond immediately. Can you understand here? Hello? Students, please respond. Can you understand? Hello?
Yes,
Hello?
sir. Yes, sir.
Okay, okay. Please respond here immediately. Okay. Now, this is the 4.3.4. Now, especially in this unit, sometimes is given. Every time is also repeated. Those theorems are repeated here. A normal linear space is finite dimensional. First of all, given the normal linear space is finite dimensional. What is the meaning of finite dimensional? Then the finite basis of the normal linear space is called finite dimensional. The number of bases is finite. That is called finite dimensional. Now that normal linear space is denoted by capital N. When it is finite dimensional, depends upon the above theorem. If and only if. If and only if means that is the necessary and sufficient condition. The closed bounded sets are compact. Now we have to take in the normal linear space finite dimensional. Then the complete is closed bounded sets are compact. Now sufficient part is given the closed bounded sets are compact, then automatically then it is finite dimensional. That is the sufficient part. Now this theorem is completely depends upon the above two theorems. Okay, 4.3.2, 4.3.3. These those two theorems must, according to those two theorems, have to derive this 4.3.4 theorem, because those two theorems are clubbed given this statement. First we are taking from the theorem 4.3.2. What is that? Closed bounded sets capital N, normal linear space N is compact, then it is finite dimensional. First of all, you have to write this one. Students, it's a very big mistake in the final examination answer sheets. Okay, some students or number of students are just you have to write the from theorem 4.3.2. That's not encouraged here. Okay, from theorem 4.3.2 means first of all you must write the above statement is there. That statement is 4.3.2 statement is there. Now that the statement you must write here, and then the remark is also there 4.3.3 on the closed that the unit sphere norm x equals to 1, that the set is compact, then automatically n is finite dimensional. Now those two statements just you have to write here, and an isometric isomorphism of a normal linear space capital N into a normal linear space n dash. So in between the n and n dash there are two normal linear space, then the connected map is isometric isomorphism. Okay. Now isomorphism means 1 onto and homomorphism when it is satisfied, when the preserved condition is also satisfied, that according to the homomorphic condition satisfied throughout the 1-to-1 mapping. Now that is called isomorphism part. Okay. Now then that isomorphism is isometric when it is isometric in between n into a normal linear space n dash. 1-to-1 linear transformation. That is called isometric isomorphism. Now that isomorphic mapping of the norm is norm x. Norm pi of x equal to norm x. That is the condition of isometric isomorphism. For every here x belongs to n is there. Now that normal linear space, when it is the isometrically isomorphic to n dash. Now if there exists an isometric isomorphism n onto n dash. Now in between isometric isomorphic relation in between n and n dash, a topological isomorphism. Topological means already we have learned in first year PG first year paper, fifth paper, topology is there. Now through the topology means a topological isomorphism in between n and n dash of the normal linear space. It is a 1-1 linear transformation, that is capital T in between n into n dash, because that the inverse of the linear transformation is also continuous, because T and T inverse are continuous on their respective domains. So n is topological isomorphic n dash if there exists a topological isomorphic of n onto n dash. So especially in this theorem is also referred, and another way of the statement is so topologically isomorphic relation n into n dash in between isometrically isomorphic relation. Prove that topological isomorphic in between n and n dash, n onto n dash. So this is also same proof 4.3, 4.3.2, 4.3.3. Now write the case 1 and case 2. And now those two theorems just you have to write in the place of this one. So then the continuous of this part, this is the theory. Okay. Students, now this is also one of the important, because so 1-to-1 linear transformation, topologically isomorphic transformation in between n and n dash, then their norm lies between infimum and supremum. Here small m be the infimum and capital M be the supremum of the values. Okay, now this is the one of the most important relation, because given the set is bounded. Now how to convey the concept of boundedness? So that set is bounded lies between the law, it having lower bound and upper bound values, and according to the set must exist means now it has infimum and supremum of the values. Now here the transformation, linear transformation through the normal linear space, defined the normal linear space of the linear transformation and connected the element is small x. So then their norm lies between m into norm x, small m into norm x, and capital M into norm x. Here small m and capital M, both values are referred in the infimum and supremum of the values. Now that is the easily to understood here. When you must understood the analyzation of this part and the basic concepts, now easy to follow the further upgrade of the theory. Okay. Now this is also one of the analyzation, that is the functional analysis. Okay. Let n and n dash be normal linear spaces, and both are topologically isomorphic if and only if. Now both normal linear space, when it is the topologically isomorphic, if and only if there exists a 1-to-1 linear transformation T defined from n onto n dash and positive real number small m and capital M, such that that transformation represents exists of the linear transformation, then their norm lies between what is that? Here small m into norm x and capital M into norm x. There are two real numbers, small m and capital M. Those real numbers referred, infimum is denoted by small m, supremum is denoted by capital M is there. First of all, so you have to take the topological isomorphic, then you must prove that this is the relation. Okay, norm T of x lies between m into norm x and capital M into norm x. And another one, converse of this part, you have to take in the another one. Here norm T of x lies between m into norm x and capital M into norm x, then easily to prove the topologically isomorphic. There are two ways, that is a necessary and sufficient part. Already we have to discuss the above the concept 4.3.4 theorem, and according to that definition topological isomorphic, if there exists here, what is the topological isomorphic? 1-to-1 linear transformation T of n into n onto n dash. When it is that transformation onto part, then the inverse of the transformation is also continuous on the respective domains. This is the meaning of topological isomorphic part is there. By theorem, already 3.4.1, what is that theorem? The four conditions are there in the third unit is there. When it is the T continuous at origin, T is bounded. Okay. So that bounded of the value norm T of x less than or equal to capital M into norm x. Okay. Now the above the T, if T is continuous, that topological isomorphic mapping is continuous if and only if there exists any one of the positive real number, capital M is there. So that is the one of the positive real constant, capital M. So that the transformation topologically isomorphic mapping, so norm Tx is less than or equal to capital M into norm x. See the third unit of the first theorem. Okay, T is continuous and T gets that continuous at origin, second condition, and third one, that the normal linear space of the mapping is also bounded. So when on behalf of the third unit of the first theorem, third condition is boundedness of this part. Norm Tx is less than or equal to M into norm x. For all here, x is also belongs to capital N. Okay. Now the same in the same manner, 3.4.3 theorem is there. So if T is, then the transformation of mapping is continuous, then the inverse of the map is also continuous. If there exists a positive real number and another real constant is small m. So inverse of the transformation, that the real constant is small m. So that is M into norm x less than, that is the reverse of the part. M into norm x less than or equal to norm Tx. For all x belongs to capital N. So given the both transformation of the part, when it is the T and the T dash, okay, see this one, T and T inverse both are continuous. There exists a positive real number small m and capital M such that norm Tx lies between small. Now that is the if and only if condition. Okay, now that is the only one way of the part, because necessary part is not separate, sufficient part is not separate. Because when you must represent the if and only if part, now at the same time both conditions are satisfied. Norm Tx lies between M into norm x and capital M into norm x. So given the normal linear space is topological isomorphic to n dash, there exists positive real constants small m and capital M such that norm Tx lies between small m into norm x and capital M into norm x. So that is the end of the proof. Very important theorem in the final examination. Don't split is there. Okay. Another important theorem. Now without this theorem you can't expect any one is there, because one is connected to another one is there. Because this theorem is students. This theorem represents in the vector spaces linear transformation. Any two finite dimensional vector spaces are isomorphic. Okay. Any two finite dimensional of vector spaces are isomorphic. Now that is the theorem in the under UG level. Okay. In the same manner, any two n-dimensional, here the normal linear space is n-dimensional normal linear space. You have to take in any two n-dimensional normal linear space over the same scalar field are topologically isomorphic. That is the statement, students. Please keep in your mind, without this theorem you can't expect the functional analysis paper in the final examination. Please note down 4.3.6. This theorem is also very, very, very important in the final examination. Okay. Any two n-dimensional normal linear spaces over the same scalar field. First of all, just you have to understood here, it is sufficient to prove that any n-dimensional normal linear space over the same scalar field, either given the field of the elements, that is the real numbers or complex numbers, when it is the topologically isomorphic to n tuples of the field represented by f power n. It read as n tuples of the field elements. Those field elements referred either real numbers or complex numbers. And write the norm is there. So you have to take in any one of the element that n tuples of the field element is alpha be any one of the field element. Okay. So then their norm represented by, what is the norm condition? Summation mod alpha I whole square and whole power 1 by 2 or square root of mod alpha I square. So it represented by square root of alpha 1 square plus alpha 2 square plus so on alpha n square. Now whole power 1 by 2 represents means that is the square root of that square root of mod alpha 1 square plus mod alpha 2 square plus 1 up to n dimensional elements mod alpha n square. So that value is, that is the definition of norm alpha. Now here alpha be the n tuples of the field element. That element is either real or complex. Okay. Now here capital N be the n dimensional normal linear space, because n dimensional normal linear space both are connective map the n and n to n, n onto n. So here that is the representative of the elements x1, x2, so on, xn, and by the element of x be a basis for n, because this is the finite basis elements given in this part. So that is called finite dimensional of the part. Now here the defined of the mapping, here the mapping means that is the transformation or functional, whatever it is. Here capital T be any one of the functional is defined from n tuples of the field and approaches to capital N. N tuples of the field elements approaches to, and normal linear space is n dimensional normal linear space is capital N, and the connected ray transformation is capital T. So you have to take in any one of the element is alpha. So write the mapping of the definition is also T of alpha equals to, what is the connected relation? That is the linear combination represented through the alpha values and in terms of x values, alpha and x. Here alpha and x is the, that is the scalar multiplication under the linear space. Alpha 1 x1, alpha 2 x2, so on alpha n xn. That is the defined part, and from defined the mapping or defined the transformation capital T from f power n to capital N. Okay. Okay, students. Please stay on the line. Are you follow this one? Can you understand? Hello? Hello, students, please respond here.
Yes, sir.
Okay, okay. Now this theorem is very most important. Please note down. Keep in your mind. Okay. Now here the relation is T alpha equals to, here the this is the linear combination, and in terms of what is that? Normal linear space of the elements alpha 1 x1, alpha 2 x2, and alpha n xn. For alpha is in terms of n values and n tuples of the field elements. Enter the n values you are taking, that is alpha. Okay, by definition it follows that first of all the transformation is 1 to 1 and onto 1 onto. Now first of all it is well defined. Second is 1 1 and the third one is onto. Okay, T is 1 to 1 and onto means here the topological isomorphic relations here capital T and T inverse both are continuous. Then it is an equivalent to that is also closed and bounded. Okay, already we now prove that T and T inverse are continuous. Then it is an that is equivalent to prove that T and T inverse are bounded. Both inverse transformation is also bounded. We are taking one of the element is alpha in n tuples of the field. We have write the norm T alpha. Now this element is also represented in the transformation norm T alpha equals to norm of T alpha means that is the this is the T alpha value. So we are applying the both sides on the norm part. We are taking the both sides norm T alpha equal to norm alpha 1 x1, alpha 2 x2, so on alpha n xn. Now we are dividing each and every scalar represented as the now it indicates the in the norm indicates the scalar field element. It represents the modulus value mod alpha 1 into norm x1, mod alpha into norm x2, plus so on mod alpha n into norm xn, because all the scalar elements in their norm represented as the absolute representation. So again you have to connect it with absolute representation is also taking the norm alpha. Now replacing absolute value by norm alpha into norm x1 plus so on norm xn. Enter these values are mod alpha 1 plus mod alpha 2 plus mod alpha n. Those values are represented as in the norm value is there. Norm alpha of in the terms of norm values of x is there. So this value is also represented. Enter this value represented is capital M, because all the norm of the values is denoted by individual of the norm values of x value is denoted by capital M. So this is M into norm alpha is there. If it is M is finite, we have norm T alpha less than or equal to M into norm alpha. Already in the same manner, T inverse is also continuous. In the above theorem is also we have derived. Norm T alpha lies between small m into norm alpha and capital M into norm alpha. And according to this one, norm T alpha is greater than or equal to small m into norm alpha, because when the given the inverse of the transformation is bounded. Okay. Now given the set is denoted by capital A, we have taken the set capital A means when it is compact, bounded, closed and bounded, then automatically that is also a finite dimensional normal linear space. Here x be any one of the element given the n tuples of the field element, then the norm value norm alpha equals to 1 is there. Here small m is infimum of norm T alpha. Now that value is greater than 0 when the given the set is closed. And norm T alpha is greater than or equal to small m is there. Greater than or equal to small m. And beta is also in the same manner. Beta is also represented in the n tuples of the field element. That element is non-zero. Now write the orthonormal of the value. Say that value is alpha from beta representation. So alpha equal to beta by norm beta. Now this is also referred in the above theorem. So many theorems are also proved there. Okay, when the given the sphere field of the element, n tuples of the field element is, then their norm is 1. So norm T is greater than or equal to small m. So replacing m by, what is that? Alpha by norm T means norm T of alpha. Alpha is also replaced by beta by norm beta. So simply norm T means norm T alpha. Alpha replacing alpha by beta by norm beta. Okay, students, just this is the very important notion. Norm T means norm T alpha is greater than or equal to m. F means f of x. Okay. In the same manner, norm T of beta by norm beta is greater than or equal to m. And when the cross multiplication of this value, norm of T beta is greater than or equal to m into norm beta. So finally, norm T of T beta is greater than or equal to m into norm beta. For all beta is also n tuples of the field element. So this implies given the inverse of the value is also, inverse transformation is also bounded. So this is the any two finite dimensional, any two n dimensional. Now already in the same manner in the vector spaces of the linear transformation, any two finite dimensional vector spaces have the same number of elements. That is the theorem in the undergraduation level. But here they especially any two n-dimensional normal linear spaces over the same scalar field are topologically isomorphic. That is the end of this proof. This theorem is very simple. Students, listen carefully. Okay. And here just you have to see and refer, especially students, this is one of the finest paper through the analyzation, that is the functional analysis. It is completely based on the real analysis, topology and complex analysis, whatever it is. And through the topology, then the continuation of the part and both are clubbed theory is there. That is the functional applications in the analyzation part. Now enter this theory much more important, especially Dr. B.R. Ambedkar Open University study material, much more reference part of that is the preparation of net exam, UGC net exam. This is one of the finest material, entire all the papers. And suppose you have to take in the post-graduation first year, algebra, real analysis and DMS. Okay. And the fourth one, differential equations, topology, and also in the final year papers, functional analysis and complex analysis, paper 7, paper 8A, commutative algebra, and 8B, applied mathematics paper. What is that? Methods of applied maths, MAM. And 9A is the measurement integration. 9B is the numerical methods. 10A and B is the operations research. 11th paper is operator theory. All the study materials in the Dr. B.R. AOU, one of the finest preparation, that is the reference part, especially in suppose if you have to apply the net exam, UGC net exam, or go to the APPS Scholar Service Commission exam. Any exam is also one of the finest material, entire the all the higher levels. Okay, research fellowship is also completely based upon the university material. Okay, now don't think otherwise. Now comparatively, any other universities is also compared to, especially Dr. B.R. Ambedkar University study material is well defined. There is no doubt. Okay. each and every. Now, just you have to take in the two norms is there. Now, why should I also represent the entire the theory is there? Okay. Now, especially this definition is also referred in the NET exam is there. NET means National Eligibility Test and Lecturer's Eligibility Test, whatever it is. Okay. UGC NET and CSIR exam, whatever it is. Now, that is also, this definition is also number of times represented in those exams. Now, here the two norms, first norm is this is the first norm and this is the second norm. On a linear space n and n are set to the equivalent if there exists a positive real constant small m and capital M. Small m is the first norm of the real constant, capital M is the second norm of the constant. So here second norm value lies between the first norm of small m and first norm of capital M is there. So second norm of the representation, second norm lies between first norm of the small m and first norm of the capital M. Now that is the two norms generated same topology on capital X. Okay, with the same topology, how to define the norm values? Okay, and there we have to take in one of the linear spaces capital N. When it is then the two norms are said to be equivalent. Equivalent means then the second norm lies between first norm of the small m value, first norm of the capital M value. That's why there are two norms generated here, same topology on capital X. Okay. Now, this is also one of the all norms on a finite dimensional linear space are equivalent. Students, listen carefully. All norms on a finite dimensional linear spaces are equivalent. All norms means norm x1, norm x2, and up to norm x1. Now, these are all finite dimensional. We have given the finite dimensional linear space means finite basis of the elements on throughout the normal linear space, and all those norms, when it is those norms are equivalent. So the above definition is, it follows that now combining all the theorems 4.3.5, 4.3.6, these two theorems, and clubbing here these two theorems 4.3.5 and 4.3.6. These two theorems involved given in the statement. Suppose in examination is given, prove that all norms on a finite dimensional linear space are equivalent, means the above two theorems through this definition. Please present the proof is there. Okay. Okay, students. Now, each finite dimensional normal linear space is also complete. Okay, each finite dimensional normal linear space means simply that is NLS is there. NLS means normal linear space. When it is finite dimensional, every normal linear space, when it is finite dimensional, then it is also a complete. So this is also the above theorem 4.3.6 and 4.3.8. From the fact that n tuples of the real numbers, we are taking the field of the elements n tuples of the complex numbers are also complete normal linear spaces. Okay, students, now this is one of the important theorem. Number of times is also these two theorems presented given in the long answer question 4.3.10, 4.3.11. These two theorems are number of times given in the final examination as a long answer question, 10 marks. Okay, or one theorem is given in the short answer question. Okay. Now, that is every complete subspace of a normal linear space is closed. So, when first of all, a normal linear space of the subspace is complete. Cauchy sequence converges to a point. That is the meaning of completeness. Now, according to the normal linear space, you have to take in the one of the subspaces there. That subspace, when it is complete, then automatically it is closed. It is there. So, that is the statement. How to study and steady. Okay, you must read as on the steady part. STEADY. Study means that is the stabilization of this part. Okay, now study, read carefully. Study means read carefully. First of all, given the statement, read carefully and as an steadiness. Okay, without this one, we can't derive the proof given the statement. Okay, every complete subspace of a normal linear space is closed. Okay, please stay on the line. Please join the line. Come on. Please join the line, students. Okay. Now, first of all, you have to take the normal linear space is capital N and G be a complete subspace of N. Now, complete subspace is denoted by capital G and normal linear space is capital N is there. So, complete subspace is closed. That is our proof. Okay. We must show that closed subspace capital G is complete subspace is closed. Now we have to take in the one of the element is say X. Here X belongs to capital G. That element is a limit point of capital G. That point is the limit point. Okay. Finite number of members. Limit point, it is completely limit point. That is the discussed by limit point theory is discussed by for the one of the great mathematician Bolzano and Weierstrass. Okay. Already we know that what is the Bolzano-Weierstrass theorem? That is the undergraduation level that is also introduced through the open sets and closed sets. Now, Bolzano, he was discussed finite number of members and Weierstrass especially, he was discussed an infinite number of members. So, an infinite number of other than the points that is called a limit point is there. Because here especially, suppose given the set is when it is a finite set has no limit point. And according to that here, given that set is closed is there. That's why just you have to imagine the one of the limit point is say X. Here X belongs to capital G. Okay, we can find a sequence Xn is also belongs to G. Any one of the sequence represented given in the complete normal linear complete subspace, that is the sequence Xn. That sequence of the convergence point is X. So that's why it represented as Xn converges to X. It read as Xn approaches to X means, and also Xn converges to X. Okay, that is the study purpose. Now, evidently here Xn, in the same manner, Xn is when it is the Cauchy sequence in what is that capital G? That is complete subspace. When it is a Cauchy sequence represented by Xn sequence, every convergence sequence is Cauchy. Already we know that. Convergent sequence is bounded, but converse is not true. Bounded sequence is not convergent. Bounded sequence is not convergent because there are so many theorems we will establish, especially we have to establish enter the analyzation part or all algebraic part. Okay, is the converse to justify? Is the converse to justify? Okay, suppose just you have to imagine one of the statement is there. Every convergent sequence is bounded. Is the converse to justify? Yes. The proper when just you have to imagine that is the proper part is established part, and converse part is not. Is it sometimes established or not? Okay, so converse of the theorem is not true because every convergent sequence is bounded, but bounded sequence is not convergent. In the same manner, every convergent sequence is Cauchy. Cauchy means a sequence is defined by Cauchy. That's why that is called Cauchy sequence is there. So, given that sequence is convergent, there is also a Cauchy sequence. So, convergent sequence means, suppose Xn be any one of the sequence, limit Xn equal to X is there. Then it implies mod Xn minus X is less than epsilon. That is the sequence of convergent. That is also represented as Xn converges to X. So, that capital G means complete subspace is complete through this statement, every convergent sequence is Cauchy, and when it is the capital G is complete, Xn converges to X. Here X be the limit point given that complete subspace. So every limit point of capital G belongs to capital G. So that's why given the complete subspace of NLS means normal linear space of the closed subspace is complete subspace is closed. So that is the very established theorem. So this is also very important theorem in the final examination as on the short answer, either short answer or long answer. And long answer is given. There are two questions is given. One question is this one, and second one is the remark is there. What is that remark? So from the corollary, the above two theorems, following the established result is there. Okay. Now here every finite dimensional linear subspace of a normal linear space is closed. So the above the part is what is that complete subspace through the normal linear space. But here that normal linear space of the finite dimensional linear subspace, that subspace is finite dimensional, that is also closed. So this is also well established. That is the simple proof. Let capital V be a finite dimensional linear subspace of a NLS, and the above the corollary, what is that? Finite dimensional normal linear space is complete. From that theory is here the finite dimensional normal linear space is complete. Then automatically finite dimensional, and the above theorem, every complete subspace of a normal linear space is closed. So then automatically finite dimensional normal linear space is also closed. Write the statement in the replacing of the theorem 4.3.10. So number of students present in the answer sheets, okay, answer books by theorem 4.3.10. That's not correct. Write the statement is given. Okay, write the, you must present the statement in the replacing of this line. Here capital V is closed. Thus every finite dimensional linear space of a normal linear space is closed. Okay, students. Now this is one of the important concept of finite dimensional normal linear spaces, and how to define the continuity of linear maps. Now that is also very simple concept. Okay. What is the here capital NB, any one of the natural mapping? What is the embedding mapping? What embedding mapping means? Natural mapping. Natural mapping is defined from capital T, defined from N onto quotient. What is that? Quotient space N by M. Students, this is one of the most important and very interesting concept, especially because already we have learned in algebraic part. What is state and proof fundamental theorem of homomorphism on groups, on rings, okay, on Galois theory, and so some other also there. Okay. Now, in the same manner, here, what is the quotient space? Through the linear space. N be the normal linear space. It is defined onto quotient space means N by M, because M be a closed subspace. Okay. N by M is the quotient space. Now, the connected map is in a normal linear space onto a quotient space. Automatically, then it is continuous. That is called natural mapping. Now, here any mapping capital T defined from N onto N by M, then the relation is here taking any one of the element is X. Here X belongs to N. So that the transformation value T of X equal to N by M means quotient space. Quotient space of the element is coset. So coset through that normal linear space element defined, that is X plus capital M. So that is the quotient space element, that is the coset. So T of X equal to X plus M. So that is T defined from N onto N by M. So that is when it is continuous linear transformation under the condition of the norm T is less than or equal to 1. So that is called natural mapping. Okay. So MBA here, that is this theorem is very important through the continuity of linear maps. MBA closed linear subspace of a normal linear space. So normal linear space is N. That is the closed linear subspace is capital M. So then the N by M is called quotient space. So connected the map is capital N onto N by M. Now through the mapping is natural mapping is capital T. So T defined from N onto N by M. That then the relation is here taking the element is X. X belongs to N. So T of X equal to what is the quotient space element? That is the coset. That coset is here X plus capital M. Okay, either left coset or right coset. But here we are not necessary here. Especially we have not necessary either left or right. Okay. Now that taking of the element is at taking at left side. So this is the left coset, but not necessary under the mention of the left coset or right coset. Here T of X equal to X plus M. Then capital T is continuous linear transformation, and the norm T is greater than less than or equal to 1 is there. That is the statement. This theorem is also very important under the definition of linear transformation. Very interesting concept because this theorem is the number of times repeated, because such a number of times. Just you have to observe in the previous papers. Students, listen carefully. It's not a joke. So that's why I must continuing without jumping. Jumped part is there. Without jumping, there are number of theorems, number of definitions on the serial wise part. Okay. So first 4 units, each and every one is important. Now, when the first 4 units, when you must understood, then automatically easily to achieve such a number of theorems and easily to achieve the final examination paper. Okay. Please stay on the line. First, we show that the transformation defined by, what is the transformation? Definition. So natural mapping is defined by, what is the natural mapping? So natural mapping definition is T from n to n by m, defined by T of x equal to x plus m. And according to this one, when it is linear, what is the meaning of linear? T of x plus y and T of lambda x. Here, replacing what element is replacing x by x plus y. So here x comma y belongs to n, and under the vector addition is closed. X plus y is also belongs to n. And according to that element of the transformation is T of x plus y equal to, by the definition, replacing x by x plus y of plus m. So this is what is the under the coset addition. Coset addition means addition of cosets means x plus m plus y plus m. That is the addition of cosets. Now that's why that is x plus y of plus m. Okay, cosets of linear spaces, cosets of linear space means linear addition or vector addition. T of x plus y equal to this value is T of x, this value is T of y. So linear, first condition of linear is verified. Second condition is under the scalar multiplication of the transformation T of lambda x, replacing x by lambda x plus m. Okay, so lambda be any one of the scalar. So that's why lambda of x plus m. So x plus m replacing by, that is the under the definition T of x. So when these two conditions are verified, that is called linear transformation. So norm Tx equal to, very simplest proof, students. Norm Tx means applying the norm under the definition on both sides. Norm Tx equal to norm x plus m. Already we know the definition of norm x plus m in the previous part. What is that? That is the greatest lower bound of norm x plus small m. Here small m belongs to capital M. So enter this value is less than or equal to norm x. So finally prove that norm Tx less than or equal to norm x. So here norm x value is that is the unit value. So finally norm Tx means norm T into norm x, cancelling on both sides, or already this is the unit sphere value. So unit value is 1 is there. So norm Tx is simply represented as the norm T less than or equal to 1 is there. So that's why given the transformation is bounded. So under the definition of natural mapping, so when it is a linear transformation and capital T is bounded. So that's why that is the continuous. What is the meaning of continuous? So given the transformation is linear and then it is bounded, when the linear and the bounded, so that is called a continuous part. Okay, simple. Now then automatically 4.4.2, this theorem is also very important, students. Now please note down. This theorem is also very important. Let's see this one, 4.4.2. Okay, each and every theorem just have to refer. Then the continuation, next continue after the completion of this class, just you have to refer one time only. Now easily to understood, and then automatically you have to remember, keep in your minds. Okay, now this is 4.4.2 theorem. That is there you have to take in any two normal linear spaces over the same scalar field. Suppose that given the capital N is finite dimensional, every linear transformation of n into n dash is continuous. So linear transformation in between n into n dash, when it is finite dimensional, then automatically it is continuous. Very simple proof. Every linear transformation is continuous. That is the simple statement. Okay. First of all, already we know that n dimensional normal linear space represented by, with norm is represented by norm dot. So this is the multiplication of the part under the norm. In between the norm is n dimensional normal linear space is denoted by, under the norm is double mod of the dot. Here n dimensional means n basis of the elements is finite. So x1, x2, so on, xn, and you have to take in the field of the elements is in terms of alpha values. So write the linear combination x equal to alpha 1. This is the linear combination under the transformation of the part. X equal to alpha 1 x1, alpha 2 x2, so on, alpha n xn. Applying the norm on both sides, norm x equal to, enter this value represented as summation alpha I xi. Okay, summation mod alpha I. Under the, to verify the norm condition, norm x1 equal to, what is the norm? Any two norms are equivalent. Already we have established one of the theorem, given the any two norms are equivalent. So that in equivalent means second norm lies between the first norm of the minimum and first norm of the maximum of the value. So first norm less than, it cannot exceed the capital M into norm x at 1. For all x belongs to n. Suppose capital T be a linear transformation, the transformation n into n dash. So applying the on both sides norm Tx equal to norm T of replacing x by summation alpha I xi. Okay, students, this is one of the most important concept. Now this value not mod alpha I. So enter this value is alpha I xi. Please correct in the replacing of this step, summation mod alpha I xi. Only here mod alpha is not correct. Mod alpha I xi, and applying on both sides of the transformation. Now finally summation alpha I into, because alpha is the scalar field of the representation, mod alpha into mod Txi. So this value represented as norm x at 1, maximum of norm Tx1, norm Tx2, norm Txn. So norm x lies between the norm x value cannot exceed the capital M into norm x. So replacing of that value is k into norm x, because k equal to capital M of maximum. What is the value of k? M into capital M of maximum of norm Tx1, so on, norm Txn. And replacing enter that value is k. K into norm x is given. Finally, norm Tx less than or equal to k into norm x. So this is the capital T is bounded and continuous. Students, this is the end of the 4th unit, because this theorem is, all the theorems are very important, especially number of times I told each and every theorem important. Without, you can't estimate. Okay, one theorem is given, because one theorem is connected to another one. So representation is very simple. Okay. Now, this is also just understanding purpose here. Find explicitly two constants, small m and capital M. This is one of the problem, such that square root of xi square, summation xi square of the norm xi square less than or equal to small m into mod x1 plus 1 mod xn. So this is the one of the problem. 5th problem is also very important. Okay. So the 4th one, any two norms R power n have the same family of open sets. Already you have to derive it here. Okay. Now the solution is individual of the absolute representation of xi values capital M into square root of x1 square plus x2 square. Here all the xi values is also belongs to R power n. Okay. Now this one is very important. Listen carefully. 5th one and the 4th one, prove that. Again repeated here. Any two norms of R power n have the same family of open sets. This is the solution. 4th one, 5th one. 4th one is number of times is given in the final examination. That is on the short answer. Okay. Any two norms means one norm is R power n under norm at 1, and again R power n under norm at 2. Second norm. So connected the map is capital T. So that is also same family of open sets defined by Tx equal to x. This is the identity transformation purpose. So T is 1, 1 and on 2. Then the norm equals to 1, because here T is a topologically isomorphism. 1, 1 on 2 when it is linear through the norm T equals to 1. That is the unit norm is there. So that's why given the transformation is under the norms, two norms, that is called a topological isomorphism. And consequently, given the capital G is open and under the relation TZ is also open under the norm at 1, norm at 2. So both norms it is also reflected here. Given the capital G is open. So family, those norms through the n tuples of the real numbers have the same family of open sets. That is the simple proof is there. Okay, students, this is the end of this unit. Please see this one. Please stay on the line. Now see this one, fifth unit. Please note down the some other important questions in the fifth unit. That's not necessary here. That is the duals of Banach space. See your textbooks. Okay. Students, only just please note down, that is the important important theorems in this unit. Duals of Banach space. Please note down. First of all, what is the norm F? Please note down. Norm F equal to supremum of mod f of x. That is called the norm value. Because here norm x is less than or equal to 1. So then their supremum of the value is denoted by norm F. So that's why this is the dual of normal linear space. This is called n star, means n star is called, what is that? Here n star are called, that is the dual space. That is the representation of dual space is denoted by n star. So B of n and R, B of n and C, because this is the field elements, those field elements are either real numbers or complex numbers under the normal linear space of the Banach representation. So that is denoted by n star is called a dual space or conjugate space. So it read as, what is the meaning of n star? N is the normal linear space. N star is it read as dual space or conjugate space. So those elements are called continuous linear functional. More briefly, that is also for functionals. Okay. Now that for pointwise scalar, now it is the vector functionals are added and multiplied by scalars pointwise. So then if the norm of functional f defined by under the addition, vector addition and scalar multiplication. So norm f represented as the supremum of mod f of x. Now that is defined from here x, then their norm is less than or equal to 1. So dual of the space is also a Banach space under the norm. So how to define the n star is a Banach space? So you must please note down here B of n and R, the set of all continuous bounded normal linear space with real numbers or complex numbers. Here n star is called the dual space or conjugate space. Now here the dual space, when it is continuous linear functionals, so then automatically f defined by through the under the addition and multiplication, here norm f equal to supremum of mod f of x, norm x less than or equal to 1. That's why dual space is a Banach space. So please note down, students, this theorem is the number of times repeated in the dual space 5.3.1. Easily to understand here. 5.3.1. N be a finite dimensional normal linear space over the same scalar field. Then every linear functional on n is bounded. So dual space n star, when given the n is bounded and dual space is also a finite dimensional and n dash have the same dimension. So normal linear space and conjugate space is also bounded and it have the same dimension. Okay. So 5.3.1, this is one of the important theorem in the final examination. Don't split here. Now easily to understand here. There is no doubt. Simple proof. Okay. 5.3.1 very, very important. Okay. And the dual of the n tuples of the real numbers is n tuples of the real numbers. Duals of the, what is the LP star? N tuples of the linear space. N tuples of the linear space. LP means P lies between 1 and 1 to infinite. So dual of the n tuples of the linear space elements, when the condition is holder n equal to 1 by P plus 1 by Q equals to 1. So 5.3.2, this theorem is also number of times repeated, 5.3.1, 5.3.2. Now these two theorems are very important, and another one 5.3.3. That is the simple understand here, because that is the due to time lag. 5.3.3. This is L1 star. Okay. Linear space on the first dimension of the dual equals to L infinitive. Dual of the L1 equal to L infinitive. That is the theorem 5.3.3. Now easily to understand, because only steps are you must present the steps only, because okay. Next one, in the number of 5.4.1, 5.4.1, dual of the LP equal to LQ. Hence the condition is P is greater than 1 and 1 by P plus 1 by Q equal to 1, because LP star means the dual of the LP is isometrically isomorphic to already you have to define this definition to LQ. Okay. Now that's enough. This is the end of this part, because these three theorems up to 5.3. Okay, 5.4.1. These four theorems given this unit. Now that's enough. Okay. Just you have to see and refer on the final examination. Okay. That's enough. And 5.5.1. That's not necessary here. Okay. Those theorems are very important, students, because that is the dual Banach spaces. Dual Banach spaces means that is the image of the Banach space. That is the purpose on the through the n dimensional of linear spaces. That is the LP and LQ. It is completely depends upon the Holder inequality and Minkowski's inequalities. Okay. Now these three theorems are very important in the final examination. If you have any doubt, please stand the line. Please stand. The line. Hello. Okay, students. Now this is the one of the important concept, that is the dual Banach spaces. Now this is the end of the session. If you have any doubts, especially in this session, already five classes completed and the remaining 3 are there. Tomorrow we will discuss the one of the important theorems. Main theorems are there are 4 theorems. Hahn-Banach theorem tomorrow we will discuss. Hahn-Banach theorem and its applications, and open mapping theorem and closed graph theorem. Without these 3 theorems are completely. Now these 3 theorems are very important in the functional analysis. One of the established theorems, especially in this paper. Okay. Tomorrow we will continue. If you have any doubt, please explain here. Please asking here. Okay. Hello. Any doubts? According to these classes, if you have any doubts. Hello.
No, sir.
Okay. Okay. If you have any doubts, please contact my number. Number of times I told here, 9989476833. This is my number. You please contact as an personally part through WhatsApp. Okay. Hello, students. If you have, okay. Thank you, one and all. Tomorrow we will meet again. Same timings as usually. Okay. Thank you, one and all. Wish you all the best and good luck. Hello. Okay. Thank you, one and all.